So now we continue with the discussion which we initiated in the last lecture, that now we are designing a counter which should count from 0, that is 0, 1 and 2, and this 1, 1 which was there in a normal binary counter sequence is to be skipped. So what we find here is that it's very obvious. We should now, in binary counters which we discussed till now, we found that there was no issue of designing for the flip-flop number 0, because irrespective whether it was a binary up counter or a binary down counter, we have found that the bit number Q0, output number 0, that is the least significant bit of any counting sequence, always toggles. So while designing for that, the question of looking at other bits of the counter did not arise. It is not that only most significant bits should depend on least significant bits. Its reverse is also possible, but in case of binary counter, since Q0 was always toggling, we tied its J and K to VCC or to plus 5 volts or logic 1 directly or high, and then we proceed further for further discussion. But it is not like this. So what should happen is, based on the current state, so designing a counter now, designing counter means what? We design in a counting sequence, since the next state depends on current state, inputs J and K will drive the next state, so outputs decide what input should be. It's a sequential circuit. So listen very carefully. In general, the discrete counter, current state 0, 0 of the 3-bit up counter, we are designing a mod 3 up counter. Mod 3 up counter. In fact, being first here and common to all branches, the contents are crunched. Otherwise, even for counter, we might have taken many other examples which we cannot now. But if you want, I will give you some links. So current state of this state, whatever it may be, so this is the first principle of designing flip-flop or designing counter. Based on this, you can design anything, every counter. Current output state of the counter should be used to determine the inputs of all flip-flops. Remember, outputs of all flip-flops can take role in determining inputs of all flip-flops, so that for given current state we get the next output state as expected. I am explaining again with so slow speed. Outputs of flip-flop Q1 and Q0, also Q1 bar and Q0 bar, because they are available, so there is no need to put a separate NOT gate, but effectively it is Q and Q0 only. So outputs Q1 and Q0 should be used to decide inputs to both flip-flops J0, K0, J1, K1. So there are 2 outputs and 4 inputs. There are 2 outputs because Q0 bar and Q1 bar are just their complementary outputs available to me for avoiding NOT gate. Otherwise, I can't treat it as a separate output. So 2 outputs Q1 and Q0 are available. Based on this, I should decide J1, J0, K0, J1, K1 such that the design should be so perfect that current outputs should define inputs such that when the clock is given, next output should come. So when Q1, Q0 are 0, 0, you want next Q0 to be 1, you want next Q1 to be 0. So you decide, so we need to decide for flip-flop number 0 separately and flip-flop number 1 separately. So Q1, Q0, 0, 0 want Q0 to be 1. So what should be Z0 and Q? Now I will explain without any assumption of expertise knowledge. We go by simple copybook style. So these are 0, 0. In that case, I expect this to toggle. Here I expect this to toggle. And here I expect this to maintain last state. I expect this to maintain last state. Here I expect it to toggle. So this is something where human beings general conscious. This cannot be defined in some artificial intelligence term. A common sense. How I can proceed. So I see that you can, means it is what we can say, it is said that the dimensions with which human eyes can view something are almost infinite as regards to such, not 3 dimensions like that, but the dimensions in which human mind can think are infinite. So once I look how Q0 should change or how Q0 should proceed, because I should not use the word change. I am now deciding Z0 K0. So I should decide Z0 K0 depending upon Q1 Q0 so as to ensure that every, what we can say, movement of Q0 is in a required manner. So I simply find here that Q0 toggles. So I can say here toggling, and it is toggling, and it is last state. So toggle, toggle, last state. So this is something, as I again repeat, that no artificial intelligence algorithm would be able to give you. Your eyes watch it, toggle. Your attention is drawn to Q1, this toggling this 0, this toggling this 0, and this last state, this 1. So this is the conclusion what we can draw is when Q1 is 0, Q0 toggles. When Q1 is 0, next time Q0 toggles. When Q1 is 1, next time Q0 maintains last state. So I can say that Q1 bar should be connected to Z0 and K0. So what should drive Z0 and K0 is Q1 bar, right? So Q1 is 0, so that time this will be 1, 1. So when this is 1, 1, when clock comes, Q0 will toggle to 1. Q1 is still 0, so this will be 1, 1, clock will toggle. Now Q1 is 1, so when Q1 is 1, this will be 0, 0, when next clock comes, it will maintain last state. So Z0, K0 is, so this is not all, in all steps is not required, simply you should, so Z0, K0 and Z1. Simply, it means there is no need for, you can write down. So, in fact, actually, I should write it here, and then I can, if those who want to verify, we can verify also. So, Z0, K0, Z1, K1. I will also write here Z0, K0, Z1, K1. So, what I have defined, Z0 as Q1 bar and K0 as Q1 bar. So what will be there? Q1 bar is 1, 1, Q1 bar is 1, 1, Q1 bar is 0, 0, Q1 bar is 1 1. So I think here the design is over because after it is again repeat this one. So next is going to repeat in the same manner. If you want, I can write one more. So Q1 is 1, J0 is 0, K0 is 0. So J0, K0, sorry, J0 is 1, K0 is 1, J01, K01, Q0 toggles. J01, K01, Q0 toggles. J00, K00, Q0 maintains continuous 0. That's all. This is something which is over now. So again J01, Q01 it toggles. That's all. Now for 1. Now how this is changing? Q1. Now how Q1 is changing? So again you look at, so for travel of Q1 you keep a close watch at Q0. For travel of Q0 you kept a close watch at Q1. So Q1 continues, Q1 toggles. Here it was toggling twice, continuing once. Here it is continuing this, toggling, again toggling. So I can write here last state, here toggle I write on the right hand side, toggle here last state. This is same thing, so only, so you need not look at here, it is again just repeating. So it is last state, it is maintaining last state, it is 0. It is toggling, it is 1. So it is also again toggling here. So our simple logic fails now. So when here is last state, Q0 0. Here it toggles, Q0 is 1. But here also it toggles. Here also it toggles. So when, so Q1 is toggling here, Q1 is toggling here, and Q1 is maintaining last state only here. So remember, you can look at, so what we want to design? We want to design what should be J1 and K1. So how the flip-flop number 1 should determine its output after given state. So to both Q0 and Q1 can play a role in deciding J0 K0 as well as J1 K1. As well as J1 K1. So you need not say that toggling is here or last state is here, so I should do only this. What I can see, I can simply say that I will look when there is toggling of Q1, toggling of Q1 is there only once. It is toggling, and here otherwise it is last state. Here last I will draw it with different colors. So twice last state, once toggle. So when toggling is taking place, twice toggle, last state. So now when there are twice toggle and one last state, so you should focus the event which is happening less. So toggling here, so last state. So last state of Q1 is maintained when Q1, Q0 are 0, 0. When Q1, Q0 are 0, 0. When Q1, Q0 are 0, 0, that time we are maintaining last state. At all other cases, we are toggling. So what should we say? So when this is 0, 0, that time J1, K1 should be 1. In other cases it should be 0. So simply I can say that Q1 OR with Q0. Q1 OR with Q0. So when Q1 is OR with Q0, when both are 0, what will happen? Their addition will be 0. So when the addition is 0, last will be maintained. If either is 1, in that case the addition will be 1, so toggling will take place. So Q1 or Q0, but sometimes we say that OR gate we avoid in designing. Therefore, when both are 0, 0 means their complements are 1, 1. So Q1 bar is 1 and Q0 bar is 1. So you can also write either Q1 plus Q0 or in a systematic manner, that is De Morgan's theorem you might have checked sometime, Q1 bar dot Q0 bar. Q1 bar dot Q0. So that should be either is permitted. Q1 plus Q0 is okay, Q1 bar dot Q0 bar is also okay. So in that case then what will happen? When both are 0, this will be 0, 0. This will be 0, 1. Sorry, this will be 1, 1 in this case and 1, 1 in this case. Now you rub this out. Rub this out. Don't look at this. 0, 0, 1, 1, 0, 0. So this is 0, 0. This is 1, 1 means this will become 1. This is correct. This 0, 0 means this will remain 0. This is correct. Now 0, 1 that time. 1, 1. So this will toggle to. As in 1, 1 toggle to this. As in 1, 1 is also. Now we are here. When we are here, this is 0, 0. So this will maintain. And this is 1, 1. So all possible things. Here also this is 0, 0. Then it's so state 0, state 1, state 2. Now this is again state 0. It's a mod 3 up counter. 0, 1. It's a mod 3 up counter. Similarly, mod 3 down counter also we can design. There are many other possibilities which are beyond the scope of our discussion right now. So we will immediately design mod 5 counter and then mod 10 counter, and I think there the counter discussion should be over. I will mention in brief what is asynchronous counter and then shift register. So now mod 5 counter, or in fact we should not go for mod 5 counter because again for mod 10 we have to go by two approaches, either mod 5 plus mod 2, or in general we can directly go for a decade counter, which is required in many applications. A decade counter. So a decade counter is having how many states? 10 states. So Q3, Q1, sorry, Q3, Q2, Q1, Q0. So 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, sorry, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0. Save the space so that all you can see 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, and then again 0, 0, 0. So this is a decade counter. Being a decade, it is obvious that it will have 10 states from 0, 0, 0, 0 to 1, 0, 0, 1, and then again 0. This state 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and again 0. So now we have to design J0, A0, J1. So all four. So it needs 4 flip-flops. So how I should J0 K0, J1 K1, J2 K2, J3 K3. So how we should go for? There is a very simple way. Look at the changes. If you find something very simple, you can go easily 0 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0. So it is directly toggling always. So you can write J0 K0 as 1 1. Now if you look at Q1, same toggle, same toggle, same toggle, same toggle, same. Now here there is one problem, and that problem is that after 9, same toggle, same toggle, same toggle, same toggle, same. So you can say like, yes, same when this is 0, toggle when this is 1, toggle, 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 but here when this is 1, it is remaining same. So you have to rethink. So now we wind up the lecture by giving you homework wherein you will come up with all possible ways. Means what should be there? This J1 and K1 should be such that if the current outputs, all current outputs can drive the inputs J0 K0, J1 K1, J2 K2, J3 K3, so that we get the next state appropriately for all 4 flip-flops. I think you should make a try on your own. If it is not possible for you, then or you want to verify, in the next lecture very briefly I will explain the designing part of remaining counter. I will explain asynchronous counter, I will explain shift registers, and that would be the end. In this weekend, that is on Saturday, Sunday and Monday, which is a holiday, we will be going for interactive sessions division wise. Thank you.